it's very important that we should know or how to solve all assignments problem, because those things will be those things will be very useful for exam. And also one announcement I just want to make, that is that I am taking usually Tuesday classes, right? So this is the sixth tutorial. So there will be two more tutorial, but supposed to be two more tutorial, that is on hopefully on 10th of September and 17th of September, next Tuesday. But there I will take one more extra tutorial, that is on um, that will be on 14th of September. That will be Saturday. So on that tutorial, I will do whatever extra thing will be there, that I will do. But okay, I mean whatever problem will be left, I hope that maybe I am not able to solve all the problem with the time stipulated given to me. So I'll do if the problem is left on um, that particular tutorial. Otherwise, uh, and other times I'll do discuss the problems related to that particular week's contents. Okay, so problem 14, assignment 4, problem 14. This is problem 14. What it is says is that the which of the following subsets of MNR are path connected. We know a set is path connected if there exists a continuous function gamma from closed interval 0, 1 to n, like let x tau be a topological space. Then x is said to be path connected. X is said to be path connected if for any 2 point x and y belongs to x, there exists a continuous map gamma from closed interval 0, 1 to x, such that gamma of 0 is equals to x and gamma of 1 is equals to y. So this is the path connected definition. And so here what is the question? Which of the following sets are path connected? Okay. So here we will prove that option A, B, C, D, all option A, B, C, all of them will be path connected, but D is not path connected. So first let's consider for B option. B option, what it says, that set of all invertible elements. Let X equals to set of all invertible diagonal matrices. Invertible diagonal matrices. So it can be written as element of it can be written as it can be written as like diagonal of x1 x2 xn, such that this is diagonal of x1 x2 xn, means this one is something like MNR. All diagonal elements are like x1 x2 xn, all other elements are automatically 0. All other means non-diagonal element will be 0. But here xi, here it says invertible, that means determinant should not be 0. So determinant is not 0 means that none of the xi can be 0. So xi not is equals to 0. So this can be unitarily equivalent to, this could be homeomorphically equivalent to 0 r minus 0 whole to the power n, because r, these elements can't take value 0. But we know that r minus 0 will have is not path connected. This is not path connected. Moreover, it has two path connected components. Two path connected component. That is not important, but this is not path connected. So if this is not path connected, then how r minus 0 to the power n will be path connected? This is obviously not path connected. Okay. So, for example, no, not path connected. not path connected. Okay, so option D is not correct. So I have to check option A, B, C whether correct or not. So first A, set of all symmetric matrices, all of whose eigenvalues are non-negative. Okay, let I have to check that option A, B, C, that I will check one by one. Okay, let A now take option A. Here X is equals to set of all symmetric matrices, set of all symmetric matrices, all of whose all of whose eigenvalues are non-negative. Okay, that means all of whose eigenvalues are positive. And this thing is equivalent. This is symmetric matrix. For symmetric matrix, this thing is equivalent. All A belongs to MNR such that symmetric means A transpose equals to A and X transpose AX is greater than equals to 0 for all X belongs to R to the power n. Because we know that uh, we know that um, because we know that this is some different fact from that we know that for a symmetric matrix, all of all the eigenvalue for a symmetric matrix A for a symmetric matrix A, all the eigenvalues of A is non-negative if and only if X transpose AX is positive. This is something called positive definite or positive semi-definite because greater than equals to 0 is also there for all X belongs to R to the power n. Similarly, there is one more fact that all the eigenvalue will be non-positive but negative if and only if X transpose AX is less than equals to 0. But if it happens that there exists an X for which X transpose AX positive but there exists an Y for which Y transpose AY is negative, that does not imply anything. That does not say that the eigenvalue can be positive, negative. That doesn't say, but yes, that will hold for a symmetric matrix. If this happens, then so this is the fact that for a symmetric matrix. So that's why this set is something like this. That okay. Now what I will show that there exists a now take two element of that set. Take so to show that this is path connected or not, this particular set is path connected or not. Take two element A B belongs to X. I have to give the path. So consider gamma from 0 1 to x by defining gamma t is equals to at or ta, not at. T is the scalar multiple. Ta plus 1 minus tb. Okay. Then clearly, for all t belongs to closed interval 0 1, gamma t whole transpose is equals to t a plus 1 minus t whole b whole transpose. This transpose this transpose t is something not this same t. Okay, this t is variable and the above t is the above t is just transpose symbol. Okay, this will be equals to T of A transpose plus 1 minus T of B transpose, which is equals to T of A plus 1 minus T of B. That means for all T belongs to closed interval 0 1, gamma T is equal belongs to X. Gamma T belongs to X, not gamma T is belongs to gamma T is symmetry. Gamma T is symmetry. Now we have to show that gamma t for every t, gamma t should satisfy this type of condition that X transpose AX is greater than or equals to 0. So that we will check. Then we can say that gamma t is a function or gamma t is well defined. Now for any X belongs to Rn, R to the power n, X transpose gamma t X, which is equals to X transpose T a plus 1 minus t b whole into x, that will be like t, this is scalar, x transpose a x plus 1 minus t x transpose bx. Now note that this particular term x transpose x This is positive, and this particular term also positive. So this full term will be greater than or equals to 0. That means for all t belongs to closed interval 0, 1, gamma t. Okay, just 1 second. Yeah, exactly. That means gamma t, for each t that this gamma t is containing x. Okay, so this gamma t is well defined, and gamma t gives a path connecting a and b. So that's all. So that's all. So that means we got a we can define a path, continuous path, a continuous path in x tau connecting a and B. So X is path connected, right? So option A is correct. So option A is correct. Similarly, we can give it similarly option B. Similarly, take X is equals to all those matrices A M N R such that trace of A is equals to 1. Okay. Then we have to show that similarly define gamma for A and B belongs to X, define gamma from closed interval 0, 1 to X such that gamma of T equals to TA plus 1 minus TB. So then clearly trace of gamma T is equals to trace of TA plus 1 minus TB. That means T into trace of A plus 1 minus t into trace of b, but trace of a is 1 because a is coming from the element x. Okay, similarly trace of b is also 1, so this will be 1. So that means trace of gamma t for all t, so for all t belongs to closed interval 0, 1, trace of gamma t is equals to 1. That means gamma t belongs to x for all t belongs to closed interval 0, 1. That means gamma t, gamma, so we can connect. So that means we can connect A and B by a continuous path in X. Why this I am writing in X? Because for every t, gamma t should be element of X. When this, if this is an topological space X, suppose, okay, just a minute, I don't know how it is written. Okay, if this is a topological space X, then for any 2 point A and B, if I want to connect A and B, we have to draw a path from A to B by a line containing X. I can't take this type of path. Okay, so I can't take this type of path. Okay, so option B is correct. So option B is correct. C, set of all matrices such that X transpose AX. Similarly, you can check. Okay. Similarly, we can check that C is also correct by giving the same type of map. Okay. Now, question number. Now, question 15. Questions 15. Just 1 minute. Let me to take the questions 15. Yeah, this is questions 15. This is question 15. What 15 says that P denotes the following subsets of MNR, and then P has one path component, or number of path component of P. That is the questions. Okay, now we know that know that for any integer, any positive integer or any natural number n, G, L, N, R is not path connected, right? That is sir proved already. Path connected. And G, L, N, R have two path connected components. And there, what are the path connected component? G, L, N, R plus and G, L, N, R minus. This G, L, N, R plus means all those elements for which determinant is positive, and G, L, N, R minus means all those elements for which determinant is negative. G, L, N, R means all those elements for which determinant is non-zero. Okay, so this is the path connected. This is the two path connected component of GLNR. So I will use that fact, and that is true for every n natural number n. Now you can see that you can take P. P, what is P? If you look at the P, that non-diagonal diagonal elements are block matrix A1, A2, A3, AN. Each AI are block matrix, and this star or something can be non-zero. These are the elements. Something can be non-zero. So here is something like P is an upper triangular elements. Okay, we can look at, we can note that, we note that, not note that, note that elements of P are upper triangular matrix, upper triangular matrices. So I will, how do I connect a path? So let's, for any element A belongs to P, A will be something like this type of A1 star star dot dot star 0, A2 star something like this, and in this way AN something like this way. Okay, this is the element, or all other element are 0. So main diagonal element, if you look at the main diagonal element are block, and the lower diagonal element are 0, and upper diagonal element can be non-negative. Sorry, upper diagonal element can be non-zero. Okay, so then, if you look at A, now consider a path, consider a function, consider a map gamma from close interval 0, 1 to P by defining gamma of T is equals to something like A1 T star, whatever the star can be, this star, and then in this way T star. Okay, this way I can write it as, I can write it not this way star. I'll write this one something like A2, A1, 2, that way A1, N. Next will be like A2, 3, that way A2, N, this way. So this will be like T of A1, 2, that way T of A1, N, 0, A2, that way T of A2N. This way it will go 0, 0, 0, like the last element will be like AN. So if you look at this map, how T is multiplied? T is multiplied upper diagonal elements above the diagonal, okay? And main diagonal elements kept it as it is. So then gamma of 0, what will be? That will be like A1, A2, that way AN, all other upper diagonal and main diagonal will be 0. And gamma of 1 will be A, this A matrix, this matrix A. So that means, and also for all T belongs to closed interval 0, 1, gamma T is an element of P, right? Because P elements are something like this way, that non-diagonal elements below the main diagonal will be 0, and elements above the main diagonal will be non-zero. So can be non-zero, not necessarily 0. So gamma T belongs to P. So gamma is a path connecting A and a diagonal matrix, block diagonal matrix. This particular gamma 0 connecting A and a block diagonal matrix, block diagonal matrix gamma 0. So number of path connected component, number of path connected component of P is equals to number of, now look at this, each AI are elements of GLNI for some NI, right? And here is actually NL, not N number of, here is actually L number of element. Okay, so here is actually L number of element, L number of block diagonal matrix are there. Okay, L number of block diagonal matrix are there. So number of path connected component of, so what I just want to say is that number of path connected component of P is how I can connect this first element. This AI is coming from GLI, right? I can write this one as something like cross, in terms of crossway, like 0 0 0 0 all element 0, second one is 0 0 A2 all element 0 is in this way, right? And this type of set, so something like, okay, something like, if you look at, just I'm just writing number of, just it will be first to write number of path connected component in the space of, in the space of block diagonal matrices, diagonal, which are of the form, which are of the from gamma 0. That means what I, so this will be like some rough. So what is the block diagonal matrices here? A1, AL, all other 0, all other element are 0, where each AI are coming from G, Li, Lni, R. Okay, so we can visualize this as a matrix space GL1R, all other element are 0, something like this way, plus dot dot plus last element will be like 0 0 0 0 0 0 GLN or LNL, right? This way I can write the block diagonal matrix is something like this way. So we can visualize, we can visualize this way. So here, this particular GLN1R, it has two components. Okay, so corresponding to each GLNR, there will be a component here in between, or corresponding to the second place, main diagonal element. So there will be two places. So here we will have, so that is equals to, so this particular thing is equals to, this will be like number of path connected component of GLNIR, right? This will be product of, this will be like product of, this will be like product of I equals to 1 to L. This will be product of all GLNI, but for each GLNI there is two component. Okay, so that means this will be 2 to the power L. I hope it is clear. Okay, so number of path connected components, so number of path connected component of P is 2 to the power L. Okay, I hope it is clear. So this is all for um, this is all for assignment 14. Sorry, assignment 4. Now I will consider assignment 5. Assignment 5, first questions. What is its first question? First question, just let me find the assignment 5. First question is, this is the first question, I think. Yeah, this is the first question. Okay, this is okay. This is the first question of assignment 5. What it says that A be a subset of a topological space X, which of the following is or are true? If A is path connected, then if A is path connected, then so is A closure. If A closure is path connected, then so is A. A is path connected if and only if A closure A bar is path connected. Okay. In last problem, the correct option is this one. This one correct option. These all are not correct. So here we will show that this first three condition of these questions, like here we will show that these first three option of the questions one of the assignment 5 are not correct. Okay. So okay. If A is, so first we'll check whether A is true or not. Okay. If A is path connected, then so is A closure. Is it correct or not? That I will check whether if A is path connected, then A closure is path connected or not. That what I will check right now. So if A is path connected, then A closure is path connected or not. Okay. So what example you can take here? Hmm. Ah, so there is an set which used in lecture that I will try to construct. So take x is equals to all those 1 by n comma y such that n belongs to natural number, and y is something like 0 less than y, this one union of all those x comma 0 such that 0 less than x less than equals to 1, union of all those 0 comma y such that 0 less than y less than or equals to 1. So if you draw this graph, what will be, this graph will be something like, okay, suppose this is 0 point, this is 0 point, and this is 1 point, and this is the above 1 point. This is x-axis and this is y-axis. Okay. Now if I try to draw, I will just try to draw this portion. I will try this color. What is it? That is first 1 comma this line. Second is this line. Third is this line. Fourth is this line. This way. No, this way. So if you look at this way, and this one will be like, so what I have drawn is that the line which I have marked in blue in here, which I have marked in blue, that is this, and the portion that this portion that I will write in drawing red, this portion is something like this particular line, but this line only, this y-axis. But if you look at the main point is that this 0 point is not considered. Okay, so this 0 point is not considered. Okay, so this point is not considered. So here what we have seen is that now consider the topology, consider the subspace topology. This is subset of R square. This particular full set is subset of R square, right? So consider subspace topology of X. Then X is not closed. Sorry, X is not path connected. X is not path connected. Proved in lecture 20, I think. Proved in lecture. Okay. Now, I think 20 or 21. But now, if I take y is equals to first two set only, this blue portion, that that 1 by n comma y, such that n belongs to natural number and y is coming from 0 less than y to 1. Yeah, this one union of all those x comma 0 such that, yeah, all those x comma 0 such that 0 less than x less than equals to 1. So this set is path connected. Why this set is path connected? And y closure is equals to x. What is y? Y is this blue line. Now we can take any 2 point of this blue line then I can always get a path connecting these 2 points. Take any point here, any point here, I will always get a path connecting these 2 points. Okay, so main point is that we can always connect a path. Okay, that can stay. I will always get path connected. So this is path connected. So this y set is path connected, but y set closer is equals to x, that is not path connected. So if a set is path connected, that does not guarantee that its closure is path connected. Option A is false. Option A is not true. So option A is not true. Now for option B, if A bar is path connected, then if option A is not true, then obviously C is also not true, because C says that A is path connected if and only. So one side is not happening means both sides, there is no chance that both sides is happening. Okay, now I have to check, and option B is satisfying or not. If A closure is path connected, then so is A or not. B, take A is equals to rational number with subspace topology, with subspace topology is not path connected, right? That I have seen. Because why this is not path connected? Because in subspace topology, if it is path connected, I mean you can take suppose q intersection 0 1. Okay, we can write it taken. Okay, let me write it here. We have already discussed though. Take q01. Let's take a point root 2. Root 2 is there. So let's take 0 to 0 to 2. Root 2 is in between 0 to close interval. But root 2 is not in q. So this set can be written q intersection 0 to root 2 union of q intersection root 2 to root 2 to 2. This set can be written as, and these two sets are disjoint. Okay, so this is not connected. So if this is not connected, so this can't be path connected, because path connectedness gives connectedness. Okay, so this is not path connected. But if I take q closer, which is equals to r, is path connected with subspace topology. So A closer is path connected. That does not guarantee A is path connected. So A closer is path connected does not guarantees path connectedness of A. Okay, path connectedness of A, right? So that means option B is also incorrect. So that means only that none of this option is correct. Okay. Next question is question number 2. Uh, which of the following sets are okay? That is proved. So question number 2. Just let me find that question particularly. This one. Oh no, not this one even. These two are done. This one. So this is questions number 2. Which of the following subsets of M are connected? So it is proved in lecture. It is proved in lecture that GLNR is not path connected, even not connected, and GLNR plus is path connected. So this is path connected, okay? So this is not path connected. So this option automatically gets out. But question is whether SLNR, and also it is proved that SLNR is path. It is also proved that it is proved that SLNR is path connected. So question 2 is this. Now question 3. What question 3 says that question 3 every finite subset of a Hausdorff space is okay. Question 3. This is already done. Yeah, this is the question. Question 3. Um, Question 3. Every finite subset of a Hausdorff space is closed. This is true. Why this is true? That I will prove. Let X, comma tau be a Hausdorff topological space. Be a Hausdorff topological space. Be a Hausdorff topological space. Take X be a point X here. We need to show X is closed. Okay, that we need to show. That means enough to show. So X minus this set, take it at Y, is open in the usual topology. Okay, open in the topology of X. Okay, so how to show that this set is so let's take Y, a point in Y, capital Y. Then this Y means this X minus X. So that means this X is not equals to Y. If X is not equals to Y and X is Hausdorff topological space, so there exists two open set U and V in tau such that U intersection V is empty and X belongs to U, Y belongs to V. I will take this one as UY and VY. Then for any Y belongs to capital Y, we will get such VY. We will get such Vy belongs to tau such that Y belongs to Vy but X does not belongs to Vy. Then also that means, and also note that also Vy is subset of Y. That is very natural. Okay, that is very, because X is not there, and Y does not contains only X. So that means if I take for union of all Y belongs to capital Y Vy, then this will contain in Y, and that is also, as every Y is contained in Vy, so that means this is contained in Y. So that means this union of Vy, Y belongs to capital Y, if I take this one as the set V, then V is an open set. V being arbitrary union of open set, arbitrary union of open set, it is open. Okay, first this is open, and also as X does not belongs to Vy for all Y belongs to capital Y, that implies X is also not even in V. That means V is subset of x minus capital X, and that is equals to y. That means there exists an open, that means for every y, that means for every y belongs to capital Y, there exists an open set Vy. Okay, that I think can be done from directly. I don't need to write all those things, I think. Just let me check once. Yeah, I think that can be. I don't need to write all those things even. For every element, there is an open set V such that Vy belongs to V, which is subset of x minus x. This is true for all x. That means y, that is y. So that means y is open. Y is open. That means singleton set is closed. So that proves the thing that every finite subset of a Hausdorff space is closed. Okay. Next is question number 4. Diagonal. That is very interesting questions. Um, just let me find it. This is question number 4. What it says that a diagonal del of is equals to this diagonal. This diagonal is closed in x cross x. What we can say about x? The answer will be x is Hausdorff and other will be not true. That I will prove one by one. Okay. Let's first to that x is connected or not. That is what. So my claim is that option A, x need not be connected. Need not be connected. This is the claim. How I will prove this claim? I have to give you some counter example where this thread is closed. Let's take excision with discrete topology. I think you can take discrete topology, and that is all. Okay. So take just a minute. I think I can take discrete topology, and why I need to do all these things. Okay. X need not be connected. That I need to take. Okay. And I can take directly discrete topology. Not connected. Option D is Hausdorff, that I will prove. X is as discrete topology. Okay. X need not be connected. Let's take X is equals to R with, okay. Okay. Let's X equals to R with discrete topology, or just give a matrix. That is what I just want to see. X, okay, I can take many way, that doesn't matter. I can take this one. X is equals to 0 1 comma 0 1 union 2 3. They're not connected, but the x cross x del equals to that, but del, whatever the del said, del is equals to all those x comma x belongs to x cross x such that x belongs to capital X is closed. This is closed. Okay, that is not a big deal to prove. I can take this, or I can take or I can take x with discrete topology. Okay, so A is not true. A is not true. Option B, x is compact or not. Okay, that I think I can take x is equals to R here. Okay, here with standard topology is not compact, is not compact, but del, which is equals to all those x comma x belongs to capital X cross y such that x belongs to x, which is actually a straight line connecting something like which it is closed. Why this is closed? Just to let me write why this is closed. Is closed. Why this is there? Here, if you look at the graph of this r square, here x square is r square. Okay, so okay, this is suppose, so this is the line, so this is the line which represents delta, and this line is closed, this line is closed. I mean, if I take every point here, and if I take a limit, or I can take what I'm just saying, that if I take a sequence of point which converges to on that point, and that limit will be also in that particular point. Okay, if a sequence converges, or if a sequence coming from this particular elements coming from this line, and then and that converges to some point, that some point will also be on that particular line. Okay, this is closed. And option C, x should have, x has discrete topology. So that is also false, because if I take here x equals to r I have taken, and in this particular case delta is r with standard topology, and in this particular set I have taken delta as the diagonal elements. So but here what you have seen is that but from so but r need not be have standard topology, sorry, discrete topology. So from example of B, we can say that R need not have discrete topology. Okay. So now option D is housed up, which I will prove. X is housed up, that I will prove. How I will prove X is housed up? Let's just write del once again, that X and X belongs to capital X cross X, such that X belongs to capital X. Okay, and X tau X be a topological space. Just tau, because same one topology here, be a topological space, and X cross X has product topology, and this is closed in product topology. Okay, closed in product topology of X cross X. This is the thing. I have to prove that to claim X is housed up. Okay. How I will prove that? Let's take 2 points X and Y coming from X, and X not equals to Y. Let X and Y and X not equals to 1. Then we have to show that there exist two open set U and V containing X and Y respectively, but that disjoint. That I need to prove. Okay. Now X comma Y, that is sitting inside X cross Y, X cross X, sorry, that is sitting inside X cross X, but XY is not sitting in delta. Now delta being closed, this particular set minus delta is open. So that means X and Y is sitting inside X cross X minus delta. Okay, that means there exists an open set W such that X cross Y belongs to W, which is sitting inside X cross X minus delta. That is the definition of openness of a set. This is the set open I am claiming, and that's why I will find and W. But by basis, as this particular collection U cross V, U and V are coming from tau of X, is a basis for the product topology. Basis for the product topology. And what the definition of basis says, that if I have a, suppose XA point is contained in a topological in a open set, then basis says that there exists an element, basis element coming from the basis, such that X should contain in WX, which is contained in W. Okay, so that is what the thing we already know. So using that one, how also? So that means there exists U and V coming from tau of X, that means open in tau X, such that U cross V, this is same topology, so we don't need to write tau X, U cross such that X comma Y is sitting inside U cross V, and that is sitting inside W, that is sitting inside X cross X minus delta. But so that means what it says, that it at least says that X is contained in Y and Y is contained in V, and but U intersection V is empty. If this is not, that U intersection V is not empty, if there exists some point Z belongs to U intersection V, that means Z comma Z is sitting inside U cross V, and that is sitting inside W, that is sitting inside X cross X minus delta. But that is not true, right? Because this particular set X cross X minus delta does not have a point, any point which is something like X comma X. This can't have any point something like this. Okay, so Z comma Z, right? So that can't happen. That can't happen because Z comma Z, I mean delta is all those type of elements, and I am removing delta. That means I am removing those type of elements. Z comma Z, X comma X, Y comma Y. Okay, so that means that is a contradiction. So U intersection V is empty. That implies that uh, that what we have to prove, that if I have 2 point X and Y which are not equals, then there exists two open set U and V such that X is contained in U, Y is contained in V, and U intersection V is empty. So that means X is Hausdorff. So that proves the option D. Okay, I hope it is clear now. Now I will let's go to the next problem. What it says that, okay, which of the following subsets of Mn are compact? Okay, just a minute. Subsets of Mn are compact. This is the problem. This is 5, right? Which of the following subsets of Mn are compact? So here, what I will show that option C is correct, A, B will not be correct, and automatically D will be false. Okay. Now, option A is SLNR. Okay. Just for before this, we will consider that MNR is similar to R to the power n square, homeomorphic to R to the power n square, not similar, homeomorphic to R to the power n square, and MNR has usual topology of MNR is and standard topology of MRR. So and standard topology of MNR is coming from the standard topology is is coming from the, or same, I can write that is standard topology of R to the power n, R to the power n square, which is same with the standard topology, which is same with the topology generated by the usual metric. Topology generated by usual metric of R to the power n square. Okay, so that means we have the distance formula. That is what I am just saying. What is that? That means if I have a point a1 a2 an square, then what is the norm of this, or what is the norm of this particularly? That norm of, or a mod, whatever the mod, a1 a2 an r is equals to root over of summation of ai square. That is what I just want to say. Okay, so this will be used. So and also we have seen that, and also we have seen that in R to the power n square, a subset is compact if and only if it is closed and bounded. Okay. So if MNR, in MNR, if I want to say that a set is not compact, I have to show either it is not closed or it is not bounded. That I need to only show. So here what I will do for A. So that means here, if just make sure that how I am taking. Suppose I am taking a matrix, just I am taking 2 by 2 matrix. Okay, these are the. So here what is this norm means? This norm means A11 square plus A12 square plus A21 square plus A22 square. this is the norm, this square root is the norm, this type of thing is the norm, or length or whatever, or the metric something in metric way. What if I say, if I take this is the element and another element is something like b11, b12, b22, these are the two elements of m and r. N is here actually 2. So then matrix, this is if I write a and this I write b, then particularly dab is equals to root under a11 minus b11 square plus a12 minus b12 square plus a21 minus b21 square plus a22 minus b22 square. This is the usual metric. This is the usual metric. Okay, and with that we'll say bounded or not. That way we are saying that whether it is bounded or not. Okay, so what I will show that SLNR is not compact. That's why what I will show that SLNR is not bounded. We will show SLNR is not bounded. That will give SLNR is not compact. That will give that SLNR is not compact. Okay, how I will show that as a take an element, take n equals to 2, take n equals to 2, and that element a is equals to something like a11, a12, a22, like this way. Then if a is in SLNR, or I can write and such that a11, a12 is equals to 1. Okay, that is SLNR. That means a is contained in SLNR. SLNR means that all those n is here actually 2. All those elements for which determinant is 1. So particularly here determinant is 1, but we can take a212 as large as we want. Okay, this is a11, a22. We can take a12 as large as we want. A12 as large as we want. So there does not exist any n such that mod of a, this is not determinant, or I will write norm of a, there is no data such that summation or a11 square plus a12 square plus a22 square, this one with square root, this should be the length, this is less than equals to, there does not exist any m such that I will write this way. That means I can take, if I take m is a fixed number, I can change a1 to bigger, I can take a1 to as much bigger as I want. So that means this is not bounded. So this is the thing playing role. So SL2R is bounded. So SLNR is not compact. So I am giving a general, I am giving an example, counter. Okay. So option A is false. Now option B is also false, because as SLNR is containing GLNR and SLNR is not bounded, and it should be bounded only when for n greater than 1. If n equals to 1, that will be single element, that is bounded. Okay, so SLNR is not bounded. That means GLNR is also not bounded. So GLNR is not compact. Okay. Now option C. Obviously option D automatically. Okay, option C I will write true to correct. So then option D will be false. Okay, C. We know this ONR means orthogonal matrices. All those A belongs to MNR such that A transpose A is equals to identity. Okay. Now if A is equals to A11, A12, or I can write A equals to just in matrix symbol Aij n cross n, then A transpose A will be something like this way: summation of A1j square. J is equals to 1 to n 0 0 0 0 summation of j equals to 1 to n A2j square. Next 0, and this way I will write A nj square. J equals to 1 to n. And this is equals to identity. This is equals to identity matrix. So that means this will be 1 0 0 0 1 that way, and 0 0 1. So this is the thing. So that means what I will say: Aij square I equals to 1 to n, j equals to 1 to n. This is equals to n, right? So for any matrix, so for any matrix, for any element A coming from this O N R, what I will say that summation of A ij square, which is the length, okay, ij is less than or equals to n, okay. So that means this will be exactly n, not less than or equals to n. This will be exactly n, okay. So that means this is bounded set. That means this is bounded set. I mean, in the matrix sense, this is bounded. This is the norm. Okay. That means ONR is bounded. If you look at how I am using this, for if I take an element in Rn, something like A1, A2, An, then what is the norm or length of this particular array? That is summation of AI square, right? So this is what I am taking. Okay. Okay. Is there any doubt? Or anything I'm not clear what I'm trying to say? Okay, I think it is clear. Okay, and everything is visible and audible, right? There is no problem, right?
Yes, sir.
Okay, thank you.
Yes, sir.
So that means this is bounded, and also we have seen that this ONR is actually closed. This also we have seen in early that ONR is closed. Why this is closed? Because that is inverse image of a singleton element. That is why it is closed. I mean, if you remember the thing that F is the map from MNR to MNR, F of A going to be the A transpose A is continuous, and this ONR is equals to F inverse of this particular 0. Just a minute. So that's why it is closed, because that is inverse image of a singleton set, right? Inverse image of a singleton set. Inverse image of a singleton set. This is closed, and if is continuous, inverse image of a singleton set. I mean, closed set is closed. So that's why one is closed. So when R is closed and bounded, so that means compare. First of all, make sure that if a set is closed and bounded, that does not always it is compact. It is, we have proved that in R to the power n, if a set is closed and bounded, then it is compact, and if it is compact, then it is closed and bounded. And in a matrix space, if a set is compact, then it is closed and bounded. But closed and bounded, it does not imply that it is compact in a metric space. Okay, so don't make confuse with yourself that in R to the power n only, in R to the power n and even in C to the power n, closed and bounded means it is closed compact, and compact means closed and bounded. But in arbitrary metric space and the topology generated by that metric, in that situation, compact imply closed and bounded, but closed and bounded does not imply compact. Okay, I think there is some counter example. So option C is correct. Okay. So question 5 is, I hope, clear. Now question 6. What question 6 actually is? Question 6 is X a matrix space, Z is a closed subset. Okay. Mm, This is question number 6, I think. Yeah. X be a matrix space and Z be a closed subspace such that there is an aim. That look, that is what I am just saying here. So here it is false. Yeah. This is the example what I am just saying, that if I take a metric space and a set which is closed and bounded, that does not imply that set is compact. Here what it says, that X is a metric space, X is a metric space, Z is a subset which is closed. Okay, and M is such that there is an M such that for any AB, D of AB is less than equals to Z. Okay, so that means this is closed and bounded. This part having an M which satisfies D of AB less than equals to M for all AB belongs to Z. That means that means this Z is closed. So note that here Z is closed and bounded, but not compact. So for a metric space, closed and boundedness does not guarantees compactness. Okay, but in a metric space, closed and bounded is compact, means closed and bounded. That is for sure. But in R to the power n, these two are equal. Okay, that's what I just want to point out from last 3 minutes. Okay, so here what I will prove, that Z is not compact. That is what I will prove. That this is false. That is what I will prove. Okay, how I will do this? Just let me. Okay, consider a set X is infinite. That X is equals to infinite set. I will take X is equals to real number. That does not. X is equals to real number, and define a metric D from R cross R to R positive. How? By D of X of Y is equals to 0 if X not is equals to Y, 1 if, sorry, X equals to Y, X equals to Y, and X not is equals to Y, X not is equals to Y. Check that D is a metric on R. Okay, and this metric is called discrete metric. This metric is called discrete metric, and the topology generated by this metric, topology generated by this metric is discrete topology. Discrete topology on R. That means with that topology, with this topology, every singleton set is open and closed. Every singleton is open, that means other automatically following that every singleton set is closed also. Okay, these are the very general fact. Okay, so here what I want to say, that there should exist a set Z and which is not compact. So take full set here. Okay, take Z is equals to full R, or take just only the closed interval 0 to infinity. Then this, or take any infinite set I can take, that doesn't matter. I can take an infinite set. or take just only this set. Z is equals to 1 by n, n belongs to natural number, right? So, and union 0 does not affect. Clearly note that Z is closed because every set is closed and bounded here. Okay, so Z is enclosed here. Okay, and as for all AB belongs to R, D of AB either it is 0 or 1. So that means this is always less than is equals to 1. That means this is bounded. So here M is equals to 1. Okay, here M less than or less than equals to 1. M is equals to 1. So that means this is closed and bounded. But Z is not compact. Why? Why this is not compact? We know in a metric space, a set is compact if and only if every sequence has convergent subsequence. But if we take xn is equals to 1 by n, then xn is a sequence in Z. Okay, xn is a sequence in Z, but xn does not converges. We know that we can know that 1 by n is converges, but note that 1 by n converges to 0 in real number, okay, or in closed interval 0 1, but this is not converges to the in discrete topology. Okay, why this is not converges? Because if we take epsilon is equals to, why this is not converges? Xn is not converging as for epsilon equals to 1 by 2. So what is the choice? That if xn is converges, that should converges to 0. That is the usual choice. But if I take epsilon equals to 1 by 2 and consider epsilon equals to 1 by 2 and consider a circle around 0, what will be those points? All those x belongs to Z or R such that d of x 0 is less than half. But as we know, d of xy is equals to 1 if x not is equals to y and 0 if x is equals to y. So that means this set only contains 0, right? So this sets only contains 0. So xn is not converging. As for epsilon equals to 2, there does not exist. So I'll show that this sequence is not Cauchy. That is what I'll show. So because we know that a sequence is converges, then it must be Cauchy. But if it is not Cauchy sequence, then it is not converges, right? So epsilon equals to, so now there does not exist any natural number n naught belongs to capital N such that xn minus or dxn, here I am talking about dxn xm is less than epsilon for all n and m greater than is equals to 1. There does not exist, make sure that there does not exist any n naught for which this should hold. Why this is not happening? Because here I'll just make sure the all indices are correct. This is n, this is m. Because if n and m are too different, I mean, if n and m are different, then obviously there should not exist, the d of nm will be 1. If I take n not equals to m, then d of xn and xm is equals to 1. That is not less than 1 by 2. Obviously not less than 1 by 2, right? So that's why this is not Cauchy. Xn is not Cauchy sequence. That imply xn does not converges. Okay, so that means Z is not compact. That means Z is not compact. So here what we have seen that a sequence seems to be that converges. Sequence xn equals to 1 by n maybe seems to be that is convergent. But that converges or not, that depends on the topology, that depends on the metric. If the matrix is something suitable, then there may converges, but in another metric it may not converge. So here sequence xn equals to 1 by is not converges in the discrete topology. Okay, that is also interesting fact. Now next of question number 7. What question number 7 says? Okay, question number 7. Is there any doubt? Yeah, this is question number 7. This is question number 7. What it says that XB is shared with two topologies tau 1 and tau 2 such that tau 1 subset of tau 2. So whether first I will prove that this option B is correct and option A is not correct. Then all other automatically will cancel out. Okay, that I will prove. Okay. However, that X is compact with tau 2. Okay, then let X tau 1 and X tau 2 are two topological space. So you can say that set are same but topologies are different. Are two topological space such that tau 1 subset of tau 2. Okay. Now let X is compact with respect to tau 2. That means every open cover in tau 2 has finite subcover. That is the definition of compactness. There is some other equivalent definition, that is what closed, bounded, those things. But in usual arbitrary topological space, this is the definition. Every open cover has convergence. Every open cover has finite subcover. That is the usual definition. Okay, just 1 minute. Every open cover has finite subcover. That is what I will prove. Now whether check whether X is compact with tau 2 or not. We will check whether X is compact with respect to tau 1 or not. That I will check. So let UI I is coming from some indexing set, be an open cover of X. That means X is equals to union of all UI. I is coming from I, and open cover of X in with respect to tau 1. Tau 1. That means all this UI is coming from tau 1 for all I belongs to capital I. This is the what I mean by open cover. Okay. Okay. Now for all belongs to, okay. Now UI belongs to tau 1 and tau 1 is subset of tau 2, right? So that means this UI I belongs to capital I, also an open cover in X tau 2, right? X tau 2. But X tau 2 is compact. X tau 2 is compact. So UI I belongs to have a finite subset, so I have a finite subset. So I have a finite subset. I have what else? So there is a finite subset of I such that union of all ui I equals to 1 to n, which is equals to x, right? But that is also happening for previous case, right? So that means there is a finite subcover of x in x tau 1 for every open cover. So that means x with respect to tau 1 is compact. So option B is correct. So that seems that option D is not correct. But I will show that option A is correct or not. That if x is compact with respect to tau 1, that x is compact with respect to tau 2. Then x is compact with respect to tau 2. Let's take tau 1 is equal, let's take x is equals to r, tau 1 or not x equals to r, take x is equals to some closed interval 0, 1, tau 1 is equals to close interval 0, 1, tau 1 is equals to standard topology, tau 2 is equals to discrete topology. Then obviously discrete topology is the largest topology, so tau 1 is contained in tau 2 always. Okay, clearly x comma tau 1 is compact, that we know compact, right? Because that is closed and bounded. But in standard topology, as closed and bounded in standard topology. But x with tau 2 is not bounded with discrete topology, not bounded discrete topology coming from discrete metric defined in above. Discrete metric defined above. So here what I am saying that this tau 2 is actually a topology coming from the discrete metric defined in above. What is discrete metric? That means d of xy is equals to 0 if x is equals to y, 1 if x not is equals to y. So this is the one, just let me write clearly. So d of xy is equals to 0 if x is equals to y, 1 if x not is equals to y. Then sorry, no, sorry, here is not closed and bounded, so not, sorry, this is not closed and bounded about, because closed and boundedness is for, that is what I just want to point out, that closed and bounded is for the usual topology, not for arbitrary topology or arbitrary metric. So here you can look at that every singleton set for every x belongs to 0, 1, for all x belongs to closed interval 0, 1 are open set x with tau 2, right? So now union of all x belongs to capital X, this set is an open cover. So this set with x is coming from capital X is an open cover, but this open cover does not have any finite subcover. But this open cover does not have any finite subcover, right? So X is not compact. Here we can't take that metric, okay? The boundedness, here boundedness, closed and boundedness gives compactness, that is usual topology, usual metric in that sense, okay? So that means option A, B is correct and A is false. That what I, so A is not true. So A is not true. So automatically other option is cancelled out because compactness of X depends on the chosen topology. That obviously it depends on the chosen topology. Okay. So now we'll consider question number 8. Okay, question number 8 I'll not I'll write here only. That question number is a does there exist a surjective continuous map F from close interval 0 1 to 0 1, close interval 0 1 to open interval 0 1. That is what question is. Does there exist a surjective continuous function close interval? Answer is no, not necessarily. No, not false. This is not true. Does there exist? No. The answer is no. Why? As a continuous function maps a compact set. Continuous function maps a compact set to a compact set, and 0 1 is compact, and f of 0 1 is equals to open interval 0 1. Why this is happening? As f is surjective. Okay, so that's why f of close interval 0 1, which is not compact. Okay, so there does not exist any such map. I hope it is clear. Okay. Okay, next is 9. That is also right. I'll not copy that question. Does there exist a continuous surjective map? A continuous surjective map F from 0 1 open interval to 0 1 close interval. Answer is yes. How can I define? Okay, I'm just first try to write it in graphically. Okay, this is x-axis, this is y-axis. Okay, this is point 0. I am taking this is 1. So let's take this is 1/3. This is 2/3. Okay. Now consider this is 1. This is 0 1. So this is the level of 1 and this is the 0 level. So let's consider a map something like this. This. Yeah. So I'm just writing this one in blue, that is gx. What I just want to make sure that is gx. How I will define that. Suppose this is the map. Okay. So you can look at, and these 2 points are not defined. These 2 points, the function is not there, but still it is getting the value from minus 0 to 1, right? Still it is getting the value from 0 to 1, right? So that is what I want to show. So as we know, there exists a continuous map G from 1/3, 2/3 close interval to 0 1, such that G of 1/3 is equals to 0, G of 2/3 is equals to 1. Any such, if a straight line joining a straight line joining 1/3 comma 0, 2/3 comma, okay, that is in reverse. Okay, that is 1 and this is 0 1. There is a straight line connecting these 2 points, right? And that straight line is this blue line what I have drawn. Straight line is such type of function. Okay, then define f of x which is equals to 1 by 3 or 1 I can take even 1 for all x less than 1 by 3 less than equals to 1 by 3, I mean from 0 less than this way, and gx for all x 1 by 3 and 0 for all x greater than or equals to 2 by 3. This way I can define. That is what I just want to say. So this type of function, so this type define this way. Okay. So there is some this type of function. Okay. Now I'll define. Now I'll consider question number 10, and that is very interesting questions. That will little take time just to find what question number 8. Yeah, this is 10. This is 10. This is question number 10. Yeah, question is prove that K is compact. That is the question. Okay, I'll prove that K is compact. This is true. I'll prove that K is compact. That is what I'll prove. Okay, let's first some fact. Fact that ONR is compact seen in above, seen to seen in seen above. We have seen above ONR as compact. ON means this is equals to all those A belongs to MNR such that A transpose A is equals to identity. This is the ONR. And um, I'll write D, not the full D. D is equals to D of I'll write specifically 1, something like this way. D of 1. All those diagonal matrices, diagonal x1, x2, xn belongs to MNR such that um, summation of xi is equals to 1. That means trace is 1. Trace of diagonal x1, x2, x1. This is. And d1 is also compact. Why this is compact? Because this is subset of r to the power n. This is subset of r to the power n. Okay, this is clearly subset of r to the power n. Okay, and because element are only n element are required, this is clearly subset of r to the power n, and that is bounded. Why this is bounded? Because this summation xi is less than equals to 1, and that is closed also. And as d1 is closed and bounded, this is check. Okay, check this one check. Note that boundedness due to trace of A is equals to 1. A trace being 1, that is the region bounded. We can take a diagonal matrix, whatever, I can take as large as possible main diagonal element. So that a diagonal space of all diagonal matrix, that is bounded. So that is closed. That is correct. Okay. But that space need not be that space need not be bounded, because I can take diagonal element as large as G1. So why that should be bounded? But if I write trace of that diagonal matrix is 1, so that necessarily bounded. Okay, that is necessarily bounded. So that's why D1 is compact. So that means then as two set is compact, then their product with product topology, then X is equals to ONR with respect to D1. Please try to concentrate this particular problem, because next two problem will be will be similar to this particular problem on the basis of same technique. Okay, so this ONR and D1, both of them are compact. Are this set is compact with product topology. compact with product topology, as we have seen that x and y are compact, implies that x cross y is also compact with product topology, right? Product topology, okay? So that's why this is compact. Now consider a function f from ONR cross D1 to MNR. How I will define this function? That f of A comma B is equals to A transpose B A. Note that B is coming from D1. That means B is a diagonal matrix with trace is 1, and A is coming from ONR. It means A is an orthogonal matrix. They note that uh, note that f of A transpose B whole transpose, which is equals to A transpose B transpose A, but B transpose B is diagonal matrix, so B transpose is B, as B is diagonal matrix, B transpose is equals to B. That means so every element of so now this is one property. Let's mark it one. Okay. Next property is that I'll just say that the image of ape satisfying all these properties. Okay, that is what I will say. Okay, image of this particular satisfy all these properties. Okay, that also, and clearly, and for all x belongs to R to the power n, A transpose B A x transpose x, which is equals to AX whole transpose B AX. Okay, now note that, but here what it says that, okay, now as, okay, here I have to say something more. Okay, that is what what I need right now. So this is the thing. Okay, this is what I will need to stop. That here what it is say that D1 I'll take diagonal element with trace 0 and xi are positive. That is what I need. I'll take here xi are positive. I'll remove this. I'll write this one. All xi are positive. Okay, and trace is positive. Trace is equals to 1 and xi are positive. That means uh, the diagonal matrix is positive definite, right? As B belongs to D1 and B is equals to something like x1, x2, xn 0, 0, and all I'll write here B is equals to something like lambda 1, lambda 2, lambda 1, 0, 0, lambda n this way, and lambda I is greater than or equals to 0 for all I equals to 1 to n. That means what I am saying that every element of B is something like diagonal matrix with elements lambda 1, lambda 2, lambda n, and lambda I are non-negative, positive, and also their sum is 1. Okay, so that's why this for every x, that means x to the power t dx is positive for all x belongs to real number, because that is what means we have seen few minutes ago that if every eigenvalue of a matrix is positive, then that is given by that for a symmetric matrix every eigenvalue is positive, then we must have x greater than or equals to 0. This is, I mean, as we know, I'll just as well that I'll write. We have seen this set matrix with positive eigenvalue, symmetric matrix with positive eigenvalue, symmetric matrix with non-negative eigenvalue, not positive, non-negative eigenvalue is equals to all those A belongs to MNR such that A should be symmetric and X transpose AX positive, X belongs to R to the power n. Okay, so now how the D is defined. Every element of D1 is something like elements of this set. Okay, so that's why we will have this one, right? So that means if this is true for arbitrary x belongs to R, so that means this will have. So that means X transpose A transpose B A X is equals to AX whole transpose B AX, which is greater than or equals to 0 for all x belongs to R to the power n, as x belongs to R to the power n, that I know. So that's why this is true. So this is the property 2, and the last one is the trace. This is property 2, last one is trace, and trace of A transpose BA, which is equals to trace of, I think I am writing a little wrong, maybe. Okay, but maybe correct, but this is equals to trace of B. This is equals to trace of identity of B, because A is, if you look at, A is coming from orthogonal matrix ONR. A is coming from orthogonal matrix ONR. So if, as A is coming from orthogonal matrix ONR, so A transpose A will be identity, trace of identity of B, that means trace of B, which is equals to 1. Maybe what I am writing wrong is that we know that this fact, trace of ABC is equals to trace of ACB. Maybe check little, or either I can just, main point is that I can switch, but that switching is some very specific property that I am not able to recall right now. Okay, something like this. I can just switch. That is what. But I can write either A on the left hand side or B on the right hand side. That is what I'm just saying. Okay, maybe I'm able to write this way, not this one. That, okay, A transpose B. This is, yeah, I think this is correct. Trace of CAB. This is what I think this is correct. So that means, so this is the property 3. So if you look at 1, 2, 3, then what we will able, looking at 1, 2, and 3, we can say for all A belongs to orthonormal matrix, B belongs to this particular set D1, F of AB, which is equals to A transpose BA, that is in the element of the set K. That is what I have proved here is basically, here what I have to prove, that K is compact or not. Okay, I have to prove K is compact or not. Here I have taken X as set, which is product of orthonormal ONR cross D1 with product topology, and that is compact. And I am defining a function f from ONR cross D1 to MNR by this way. And we have seen that range of f is contained in, so that means range of f is contained in K. So f is from ONR cross D1 to K is a matrix, and this is a map. This is a map. F of A comma B is equals to A transpose B, and F is continuous. Now we will show F is surjective. For any matrix M belongs to K, M transpose is equals to M, that is symmetric. Trace of M is equals to 1, and um, X T M X is positive. Okay. For a symmetric matrix, we know this is diagonalizable. That is what. So M is diagonalizable, and if M is diagonalizable, there exists an orthogonal matrix U such that this is diagonalization. M is equals to U transpose D U, and D, there exists orthogonal matrix and a diagonal matrix. and a diagonal matrix T such that M is equals to U transpose du, as X transpose A greater than equals to 0, that means all the eigenvalue of A are non-negative and trace of M is equals to 1, that means all the eigenvalue, all the diagonal entries of D are non-negative and trace of D is equals to 1. That means D is belongs to this particular collection D1 and U is belongs to ONR. So f of this U comma D is equals to M. So what I have, okay, this is what I have used here is that diagonalization, that if a matrix is symmetric, then it will be diagonalizable. There exists an orthogonal matrix U such that U transpose D U, and this D particular will be a diagonal matrix, and the diagonal entry will be like this D particular will be diagonal matrix, and this diagonal entry will be the eigenvalue. Now, as A is such that the all the eigenvalues are non-negative, that means all the entries of D will be non-negative, and trace of A is 1. So, all trace of D will be 1 because that is the sum of eigenvalue. Okay, so that means so F is surjective continuous map from X to K, as X is equals to ONR cross D1 product of two topological space compact product of two compact space is compact, and f of x is equals to k is compact. So this is very interesting. This type of problem just you have to little change this way or that way, then you will have this type of problem. Okay, now what I will prove here for 11. Okay, 11 I will prove at least 11. Okay, I'll prove 11, and after that if I get time then I'll prove 12. Okay, now let's 11. Now this is clear now. If there is any doubt you can ask. 11 problem says that okay, lambda less than 2. This is the 11. Okay, which of the following set are compact in MNR? Set of all upper triangular matrices, all of whose eigenvalues satisfy mod lambda less than equals to 2. So first option A is not. Why A is not? Similarly, upper triangular matrices whose eigenvalue should be less than equals to 2, mod of less than equals to eigenvalue such that mod of lambda less than equals to 2. But the only element, take n is equals to 2 here, and take n equals to 2 here, n equals to 2 here, and a is equals to something like a11, a12, 0, a22, such that a11 mod less than 2 or a11 and a22 should lie in between. A11, a22 should be minus 2 to 2 close interval. Then we can choose a12 as large as we want by similar technique. Then A need not be bounded. Okay, the space of the matrix of type A need not be bounded. So then the space of the here all eigenvalues are a11, a12. So a11 or a12 are lying between minus 2 to 2 close interval. So space of all symmetric matrices with not symmetric, not sorry, space of all upper triangular matrices, not symmetric, space of all upper triangular matrices eigenvalue mod lambda less than equals to 2 need not be bounded, so not compact. Here is also we have the usual topology coming from the real number r to the power n square. So this is not correct. Now B. So the set of all symmetric matrices, all of whose eigenvalues satisfy mod lambda less than equals to 2. So here I have to take set of all symmetric matrices, all of whose eigenvalues satisfy mod lambda less than equals to 2. This is correct. This is what I think. This is what bounded. This will be the correct option. Okay, just okay. Set of all symmetric matrices. This will not be. Just only a little bit. Just okay. Let's take B a set X is equals to all those A belongs to M and R such that A transpose is equals to A and eigenvalues of A satisfy mod lambda less than equals to 2. Then I will give that this is compact. I have to show. Okay, so I have to show that this is similar technique whatever I have used in early. That is what. So take A N R and D here. I will take D of minus to 2. This is symbolical. All diagonal diagonal matrices with diagonal entries matrices with diagonal entries lie in minus 2 to 2. That means this will be something like diagonal of x1, x2, xn that is coming from MNR such that xi should lie between minus 2 to 2. That is what I am taking. So you can take this set is closed. This is closed and bounded. So this is compact, okay? And this is also compact that we have seen earlier. This is closed and bounded. So that means X is equals to ONR with this particular product is compact, okay? With product topology. Product topology. That means if I give a function f x to MNR by f of a comma b is equals to A transpose B A, then similarly what will show that the image is contained in this particular set X. Okay, I'll take here this is some different y, this is y, while say, then we will show that so that f of y is contained in X and f from y to X be a continuous and surjective map. So f should map complex set to compact set. F of y equals to x is compact because y is compact. Y is compact means that its image should be compact. That is what I will prove. But I will not write many thing here because that is exactly similar to the previous one. So this will follow this way. I'll just so what I need to show. We need to show that I'll just so what else first note that for any AB for any just 5 more minutes I'll take for any A belongs to O, N, R and B belongs to this diagonal, what we can say that A transpose B A, note that all the diagonal entries are positive. Okay, that does not imply, that does not depend diagonal matrix. So A transpose B A whole transpose is equals to A transpose B A. This can be written as 1. And second thing is I have to show that, so this is eigenvalues of A are minus 2 to 2. So similarly, if lambda is an eigenvalue of a matrix A, not the matrix A, if an eigenvalue of A transpose B A, this matrix, then there exists a lambda, sorry, there exists a non-zero vector V non-zero which is coming from R to the power n such that A transpose B A V is equals to lambda V. That implies A transpose B A V is equals to lambda A V. I have multiplied A on both sides, and A transpose is identity that as it is orthogonal, as A transpose A is equals to identity. So that means lambda is an eigenvalue of A. So similarly, sorry, if lambda is an eigenvalue of B. So similarly, if lambda is an eigenvalue of B, it is eigenvalue of A. So that means eigenvalues of B same as eigenvalues of A transpose B A, right? So as B is coming from this particular set D, eigenvalues of A transpose B A is same as eigenvalues of B which is subset of minus 2 to 2. That is what the elements of B means. Okay, so that means for all A belongs to O N R and B belongs to this set D minus 2 to 2, F of A comma B which is equals to A transpose B A sitting inside the set X, which is I have taken this set X, okay. So that means F from Mn R to X first, and similarly for any M belongs to similar to the last question, for any M belongs to X, there exists U belongs to orthogonal matrix O N R and then diagonal matrix D coming from this D minus 2 to 2 such that F of U D is equals to U transpose D U which is equals to A. So F is surjective. So that completes the proof, and F is surjective and continuous. Why this is continuous and F is continuous? Note that this completes the proof. Why? Because so okay, I'll just complete this particular question. Okay, what is this completes the proof? Why? Because why F is continuous? Because F is something like sending polynomial. Okay, elements are something like polynomial, so that's why F is continuous. So that's why this set of all symmetric matrices, all of whose eigenvalues satisfying. So option B is correct. So option B is correct. And the set of all diagonalizable matrices, all of whose eigenvalues satisfy mod lambda less than equals to true, that will not be also true, because C take matrix A is equals to A11, A12, 0, A, or I can take this will be like -2, 2. Then A is diagonalizable, but we can choose A12 as large as we want. So this type of matrix space, this type of the space of this type of matrix not bounded matrices is not bounded, so not compact. So option C is false. Similarly, option set of all symmetric matrices, that is obviously false, because we can do as large as we want. Okay, that is not a big question. Set A equals to A11, A12, A12, A22. Symmetric. This type of matrix space is not bounded. I'm taking here only 2 by 2 matrices only, but not necessarily it is 2 by 2. Is it say 2 by 2? This is for arbitrary, so I'm taking n equals to. So space of this type of matrices is not bounded. Okay, so D option is also not correct. Okay, so of 11 is done. I will not do 12, question number 12 in the next class. Till now, is there any doubt? If is there any doubt, please raise it. Otherwise, I will stop here. Yeah,
Sir, explain question number 8 once.
8. Okay, just one minute. Question number 8. Question, okay, 7, 8. Okay. 8 is the question. Does there exist a surjective do you have the question available, right? Does there exist a surjective continuous map F from close interval 0, 1 to open interval 0, 1? Right. That was the question. Okay. Am I audible?
Yes, sir. Yes, sir.
Huh. So if there is a theorem, there is surjective continuous function maps, not surjective, a continuous function maps a complex set to complex set, right? Now as it is surjective, so what is the image of this 0, 1 close interval? This will be open interval 0, 1, because that is surjective, right? But F is continuous. So F should map a compact set to compact set. But open interval 0, 1 is not compact. Why this is not compact? But because that is not closed. Is it clear? Or should I explain some differently? Is it clear?
Yes, sir. Yes, sir. Tell me.
Because why? Just let me say once again. 0, 1, closed interval 0, 1 is compact set, because that is closed and bounded. But open interval 0, 1 is not compact, because that is not closed. Okay. But in R, a set will be closed and bounded if and only compact. That is what it means. And a continuous function should map a compact set to compact set. But here F being surjective, what will be the image of closed interval 0, 1? That will be the open interval 0, 1. But 0, 1 is not compact. If there exists some such continuous function, so this should be, I mean, F should map complex set to complex set, but here F is not sending a complex set to complex set, so there should not exist such continuous function. If there exists continuous function, so F should map a complex set to complex set. Okay.
Okay, sir. Okay.
Is there any doubt? Any
Sir,
other doubt
9
before?
also. 9, 9.
9. Okay. 9 is reverse. 9 is saying that whether does there exist a continuous surjective map from close interval 0, 1, sorry, open interval 0, 1 to close interval 0, 1, right? So here
Close
what
interval
I have
0, 1.
given,
Yes,
this
sir.
type of function, if you consider that this is the line what I have drawn, this is the line. Okay, if you can draw this type of function, you can take that at the point 1 by 3 function is taking value 1, and at the point 2 by 3 function is taking value 0, right? So that means range should
Yes, sir.
contains, and in between 1 to 2, 1 by 3 to 2 by 3, it is taking every value from this way. But obviously that means it is taking every value from 0 to 1, this 0 to 1, right? Because this 0 to 1 every value is taking, right? So that means if I take any point from 0 to close interval 0 to 1, take this is the point, I can draw a line. So corresponding this point,
Yes, sir.
corresponding this point image will be that point. Okay, so suppose I have taken 0 less than 1 less than 1. So obviously that x inverse image of that x will be this one if this is the x. I hope this is clear. So that means f is taking f is taking every value from close interval 0 to
Every
1,
value between. Yes, sir.
0 to 1, and also f is continuous. So every value is taking 0 to 1 means f is surjective. That is what I mean. And f is continuous because that is continuous. Continuous means that you can look at this is there is no gap. In general, real analysis, this is something like. But okay, we can always. I have given some
Yes, sir.
construction that we can construct a g which is continuous. So this one is continuous, and I will define this one. So that will be continuous always. Though this fx is not same with this fx, because this fx will be same if this line is changed to this line. This if the left hand side line, I'm just saying if this line is given as this particular line. Okay, I think what I mean this fx means I will just write this fx means this is the graph. This is 0, this is 1, this is 1 by 3, this is 2 by 3. So this is the gx, suppose this is gx 1 by 3 to 2 by 3, this one and this one. This is the graph of fx here, complete fx taking from 0 to 1 by 3, always taking value 1, and from 1 by 2 2 by 3 to 1, always taking value 0. Clear?
Okay, sir. Okay.
Okay. Any other doubt?
Yes, sir.
Any other doubt?
No, sir. No.
Okay, now.
Okay, sir. Thank you.
Thank you. So I'll stop here. Okay.
Okay, sir.
Yeah. Thank you.